In 7.3, we continue working with differential equations with real-world applications. So same essential question, how do you write and solve differential equations? So just more practice with these. They're going to get a little bit more complicated, but not much. So let's start by just doing a really simple example. And then we'll do the exploration. We're going to write as a function of w in terms of t. And so we'll have this differential equation that is dw over f minus k times w equals dt. Okay, well, let's remember in this that, our variables are basically w and t. So that means that f is a constant, as is k, and k is that proportionality constant. Okay, so when I'm working with this, it's probably going to be easier to look at this if maybe I said, well, this is really 1 over f minus kw dw equals dt. Right? Because now when I take the integral of both sides, I can see that this is a reciprocal function, right? So that tells me that if I'm taking the integral with respect to w, that's just going to be the ln of the absolute value of f minus kw. And then I would have to think about, the chain rule would happen to that. So unchain ruling it, I should multiply then by a negative. I should divide by a negative because that's a constant, 1 over k. Right? Imagine maybe that was like 4, so I'd be dividing by a negative 4. So I'll just write that out here. Now on this other side, whatever I took the derivative of was with respect to t. So what did I take the derivative of to end up with just 1? Okay, so that would have to be t. And then plus my constant. Okay, so from there now, what we're going to want to do is we're going to kind of rewrite this. So why don't I start by getting k onto this other side? So I'll have ln of f minus kw equaling, well, that's a negative k times t plus c. Right, my goal here is to get w in terms of t. So I got to figure out a way to get w out of all this mess here. I'm going to go ahead and distribute this negative k. So I'll end up with ln of f minus kw equals negative kt plus a negative kc. Now I'm putting the plus there for a reason, and you'll see this in a minute, and we did this in our last section as well. Because now what we're going to do is we're going to undo this ln, right, so that I can get this out of here. So I'll basically rewrite this as an e to this side. Oops, minus. And so what we have said in the past is that then this can be rewritten as, the product of two base e's, right? Because whenever you multiply like bases, you add exponents. So this is really e to the negative kt times e to the negative kc equals the absolute value of f minus kw. Oops. Okay, so now what I want to do is I want to get rid of these absolute value signs. Okay, so what ends up happening is, if I want to get rid of this, I can say, well, then this side is either going to be positive or negative. Okay, but what we have to realize is that this right here becomes a constant. I'll call that constant 2. It's some number, right? You've got e being raised to a constant and a constant. Constant times a constant. So it's some constant. We don't know what that is. We'll let that determine the sign. Okay, remember, anything with a base e, well, that's a base that's bigger than 0, so that's a function. That's a growth. That's an exponential growth function. So we'll let c decide whether this side's going to be positive or negative. Okay, so I really just throw that out. I throw out the negative. I just leave it. It's going to be positive. Oops. Unless c tells us otherwise, or c2, I should say. Unless our constant tells us otherwise. And we won't know that until we have some more points to plug in. Okay, so instead of leaving this as e to the negative k over c, I'm just going to leave it as some constant that I don't know. So now I can rewrite this side as c sub 2, or my constant. And I'm using sub 2 because I already had a c. So we'll use a sub 2. Times e to the negative kt equals f minus kw. Okay, so now my goal is to basically get that w by itself. So let's see. So one thing I can do is how about if I bring this kw over here and I'll subtract, just trying to keep, my w positive. So I'm going to say, okay, well now I've got kw equals f minus c2 e to the negative kt. And then I just need to get rid of that k. So I've got w equals f minus c sub 2 e to the negative kt all over k. Now, I know you're asking yourself right now, can we just use a number at some point? We've got a number in here. It just happens to be represented by a letter. And all of these other things can have a number too. We just don't have those numbers just yet. All right, so let's do, I gave you guys an exploration, and we're going to work through that together. All right, so let's see, am I going to have enough room on this piece of paper? Probably not. Oh, let's try it. I'll kind of be writing some notes all over the place. Let's see if I can zoom out. So not the best copy I could make, but good enough. All right. So we've got Ira member is a freshman at a large university, and one evening he attends a reception at which there are many members of his class whom he has not yet met. He wants to predict how many new names he will remember at the end of the reception. And you're probably, telling Ira, get a life, right? Well, it's a good way to deal with rates of change, and that's what calculus is all about. So we're going to use rates of change in differential equations to come up with a model. All right, so Ira assumes that he meets people at a constant rate of r people per hour. So we need to, define what we know, and we need to keep track of all of our variables. So I'm going to let r be the people met per hour. Okay, now unfortunately he forgets names at a rate proportional to y. Okay, so we need some variable that's going to be representing the rate at which he forgets names. So we'll let that be f. How about that? Rate he forgets names Okay, so now what does y represent? Well, y is the number of names he remembers. Okay, let's see. We got that. So we're going to now, the more he remembers, the faster he forgets. Okay, so those rates are interrelated, right? One's dependent on the other. So let t be the number of hours he has been at the reception. Notice how I label all my variables so that they make sense, right? And so that I can go back and make sense out of this problem. Okay, let's see. What does dy dt equal? So that's what we don't know. Use the letter K for the proportionality constant. Okay, so let's go back to the part of this that talks about proportionality. So it says here that he forgets the names at a rate proportional to y. All right, well, that means that his rate of forgetting, which is f, is going to equal some proportionality constant times y. Okay, so now let's think about this. So dy dt is going to have to be the rate at which he meets people per hour minus the rate at which he forgets names, right? Okay, so that's the change in y, which is the number of names that he remembers. So this number of names that he remembers is going to be the number of people he meets minus the number of people whose names he forgets, or the rate at which he forgets those names. So we can write ourselves a little rate, right? Okay, the change in the names and the number of names he remembers with respect to time is going to be, it's basically going to be the number of people that he meets, okay, minus the rate at which he forgets those names. Or in other words, let's come up here, dy dt, just plugging something in for f, instead of using f, I'm going to use the proportionality constant. The rate at which he meets people minus the rate at which he's forgetting those people's names. Okay, so let's go to number 2. So the equation in problem 1 is a differential equation because it has differentials in it, right? It's got the dy's and the dt's, okay? So derivatives, right? Rates of change. By algebra, we're going to separate those variables so that all terms containing y appear on one side of the equation and all terms containing t appear on the other side. Well, it looks to me like, you've got this whole side that is basically has the y in it, okay? And then you've got the dt, which has the t in it. Okay, so what I'm going to do is I'm going to divide both sides by this side so that I can bring this over to the dy side. And then I'm going to multiply both sides by dt so that dt ends up over here. Okay, so what I end up with is really 1 over r minus ky dy. And why am I writing it like this? Because this will show me that it's a reciprocal function, right? And then on this side, I've got dt. Okay, I think that's good enough for that. And then for number 3, we're going to integrate both sides of the equation in problem 2. And you should be able to make the integral of the reciprocal function appear on the side containing y, which is exactly why we set it up this way. Okay? If you just had dy on there, it might be a little bit more confusing. So your goal is here to, get a reciprocal function so that you can take the integral of that. Okay, so integrating both sides then. Actually, I'm going to write that up here just so that I have some proper notation, but then I'm going to follow up down below just in case I don't want to run out of room. So I'm basically just taking the integral, indefinite integral on both sides. Okay, so that tells me that I'm going to end up with the ln of r minus k times y. And then again, thinking about that, I'm going to need to do that derivative or anti-chain rule. I'm going to need to multiply. I imagine that was, again, negative 4y. Well, I'd need to divide by negative 4. So out in the front, maybe I'll give myself a little bit more room here. I'm going to go ahead and multiply by a negative 1 over k. Okay, so doing that on that side, And then on this side, well, what did I take the derivative of to just have with respect to t? I had to have had a t there. So I'm going to do a t plus c. Then I'm going to, I'm working on, trying to get this so that, well, let me rewrite the directions. Integrate both sides of the equations. You should be able to make the integral of the reciprocal function appear on the side containing y. I think we're probably good right there. Let's actually stop because I believe the next part has us do more work. Okay, I might come back down here and keep working only because I don't know if I'll have enough room up here. So show that the solution in problem 3 can be transformed into this form right here. Okay, so this is where we're going to try and get, ky on one side and everything else over to the other side. Okay, so I'm going to actually go ahead and continue from here. So the first thing I'm going to do is I'm going to multiply both sides by negative k. So I'll have ln of r minus ky, or absolute value, sorry, ln of absolute value of r minus ky. And then I'll do negative kt plus negative kc. Okay, now from there, in order to rewrite this without the ln and start trying to get rid of these parentheses so that maybe I can get, or sorry, those absolute value signs so that maybe I can get ky all by itself, then what I'm going to want to do is undo the logarithm. So using the definition of logarithm, I'll say, okay, this is really e to the negative kt plus the negative kc equals absolute value of r minus ky. Now from there, I'm going to take that product rule of exponents and realize that I can rewrite it like this. And then from there, I'm going to say, well, really, this is going to be a constant. And I'm going to go ahead and call that constant 2 because I already had a c there to give me my constant. Okay, so what I really have then is c sub 2 e to the negative kt equals the absolute value of r minus ky. Okay, so now I'm going to go up here to finish. So from here, this is where, to get rid of that absolute value sign, you're going to put a positive or negative. But really, in order to figure out whether or not it's positive or negative, we need to figure out what our constant is. Okay, so that's going to tell us whether it's positive or negative. We can't just say, oh, this ends up becoming a negative or a positive. We don't know that. Okay, once you know some points and you start plugging points in, then you'll know whether or not your constant is positive or negative. Hopefully it's not a decay. Hopefully he's not, forgetting more names than he's remembering. All right, so coming over here, then I'm just going to go ahead and rewrite that. Oops, and then it looks like from there what I can do, instead of eventually dividing by a negative, I'm just going to bring the ky over here and then subtract the c2. And they didn't use the c2, they just used a c. It's the same thing though. I'm just differentiating between the different ones. So I'm going to have ky equals r minus my constant times my exponential function with my proportionality constant in there. Okay, so now we're going to use the initial condition when y equals 0, t equals 0 to evaluate the constant c. So this will actually tell us what our c is. Okay, so let's see. So I'm going to plug in, this will be k times 0 equals r minus c2 times e to the negative k times 0. So let's see, I get 0 equals, and this is going to be r minus, and this piece right here, well, that's e to the 0, which is really just 1, so minus c, or our constant, whatever our constant is. Okay, so that basically tells me that my constant is going to equal r. Okay, awesome. So now what I can do, let's see, you to evaluate the constant. Oh, that's all they've asked me to do. It's always good to go back and reread the question. So suppose now that Ira meets 100 people per hour and that he forgets at a rate of 4 names per hour when y equals 10 names. Write the particular equation expressing y in terms of t. Okay, so there's a whole bunch of variables or constants that I know. Okay, so first of all, suppose he meets 100 people per hour. So I'm going to write it over here. So we know that R, boy, I'm having pencil trouble today. Suppose that R then is 100. Okay, and he forgets at a rate of 4 names per hour. So that means that our F is going to equal 4. And we know that y is going to be 10. Write the particular equation expressing y in terms of t. Okay, well, we knew that, let's see, F was going to equal k times y. So we know that F is 4 equals k times y. Oh, and we know that y is 10. I'm sorry. Let's go ahead and put that in there. So k times 10, which tells us that k must be 4 divided by 10, or 2/5. Okay, so now I do not have enough room, so I'm going to go ahead and grab another sheet of paper. I think I'll just do it on the back of my notes if I can find them. Ah, they're down here. Okay, so let me go ahead and start with that. So I've got k being 2/5. And I know that, let's see, here's my equation that I should be using, okay? And I know that C is going to be the same thing as R, okay? So really my new equation that I could be using is ky equals R minus RE to the negative KT. Okay, so let's see what else I've got here. So I know what R is, that's 100. I know what K is, it's 2/5, so this is really 2/5 times Y equals 100 minus 100E to the negative K and T. So rewriting it, that's 2/5 Y equals, I'm going to factor out 100 here, times Y minus E to the negative KT. I'm also going to, I know what K is. I should plug that in right there, which is going to be a negative 2/5. I could have done that up here. I just forgot. Okay, and so then the last thing I'll do here to get Y all by itself is multiply by the reciprocal. So Y equals, well, 5/2 will give me 250 times 1 minus E to the negative 2/5 T. All right, let's see. So I think I've got it completely done for number 6. And then the last thing we need to do is number 7. So let me label this. So this is number 6. And then number 7. How many names will Ira have remembered at the end of the reception? So when t equals 3. So I'm going to take my equation that I got in the last problem. And I'm just going to plug in a 3 there. And then if you put that in your calculator, you'll get approximately, let's see if I did this earlier. Yep, 175 names. It ends up being like a little bit over that or a little bit under that. I just rounded. So it's an approximation. Anything else? I think that's it. And then you can answer, what did you learn as a result of doing this exploration? Hopefully you had a couple of aha moments.